All right. Let me go back a little bit review from what we have done from Monday, last Monday. So yeah, we are discussing the limit, right? Limit as a concept. And for now, you already understand that the limit is a concept for, so basically if you have, so if you approach something, so limit is basically a concept, okay? So when I've told you these definitions, that means I have this graph here, and I have a open hole in this point here at some number here. If we are approaching from left, from right, it's going into a number, exact number, right? So that's basically when we are dealing with limit. We know the limit, but the possibility for the function to have the results is basically it doesn't need to be having a result of a function here, okay? Because it's an open function, undefined at this point, right? But the limit exists. Okay, that's the thing you need to remember. So to understand the concept, like for example, the instant rate of change or instant velocity, you need also to use the concept of limit. Okay, so you yeah. Wait a minute for QR code. So getting closer to something, making more and more approaching to some number, although it's not the number itself. That's basically what the limit is. Okay. So another application is when we are thinking on a geometric formula, we can also approach geometric formula using limit. Like for example, this one, we have a polygon and we can try to approach the polygon into circles. Like for example, let's say we have this is limit as the height of the triangle here, and the height of triangle, if you are looking here, the height is becoming more inclined with the radius. So let's say the limit as h approaching r. So that's why when we have this as our formula here, we can approach h into r, and then we can have this. Okay? And ABN here, pretty much this is the sides of all the polygons, and then we can approach them when n is getting larger. When n is getting larger, then the polygon will touch the circle, right? And when the polygon touch the circle, means it is the circle circumference, which means this one. And you know, from here, we know that we prove that, okay, the area, or maybe let me write here. So the area will be pi r squared for the circle. Okay, so we can also use the limit for some concept to approach like geometric and numeric approximations, and some other concept. Like the most obvious one is, of course, when we learned a derivative and integral, we need the limit concept to understand. Okay. All right. Just a few small remarks for the last Monday class. Okay. And then we have some games. Okay. Which of the following statement is false? So if you see here, increasing on 0, 2, so 0 here, and 2 is around here. So it's increasing, right? It's increasing. And the range is -2, -2 to 3. So -2 is here, and 3 here. It's correct. It's the range. And then, the value of x for which g is 3, g equal 3 is -4. So which means it's here. It's -4, right? Probably you missed this because you don't understand, or you need to take some time to understand the meaning. Some of you, I think. Okay, so yeah, gx3. So what is x? That's basically the question. Okay, so if you look here, gx3 is here, right? This 3. So this is 4, -4. So that's true. So the one only that is wrong is here. If we look, the domain is not the domain. It's not complete. The domain -4 until 2, and then 2 to 4. Okay. So we can just say from -4 and then including 2, or we can say -4 to 4. Okay. All right. And then this, is it true that f equals g? Do not make this mistake. Okay, so you have and you think that, okay, oh, it's equal, right? Also, it's the same. No. In terms of equation, that's the same. But in terms of function, this is not the same. Okay. Okay? Because at x equal 1, f is undefined, right? All right. So when you draw the curve, there will be difference, right? Okay. So that is why it's false. Okay. And then I think this is pretty much easy. This is the inverse. The inverse is not a reciprocal functions. Okay. So of course this will be false. Okay. All right. Okay. Attendance one more time. Please scan the QR code. Okay. If you just come, so please scan the QR code. Okay, let's move on. All right. Okay, now before we start, I have this tree graph here. Okay, this is just to remind you what the limit concept is. Okay, the first one, the graph is so smooth, there's nothing wrong about it, right? The second one, there's a hole, okay? And the third one, it's having a hole and it's having another dot here, which means at some point here, let's say at point A, we have maybe B. Okay, so we say that this is equal this. Okay, but if you look this tree, all the tree curve here, they have same limit. Okay, same limit. The limit as x approaching A of the, let's say, the function, let's say this function f of x, all will be the same. Let's say naming all the same function there. So the function, the limit will be L. This also L, although the function, when you put A inside, it's undefined, right? And then the last one, the limit is also L, okay? Although you have, when you plug in A, it's equal B, right? Okay, so this is just to keep in mind that the limit can be exists, although the functions is undefined at that point, okay? Or maybe different results from the limit, okay? Okay. Okay, another thing about limit, and I think some of you are already familiar with the L'Hopital rules. So I will give you some brief explanation. Although L'Hopital rule will be in the next chapters, not in this chapter, I will just give you a brief preview about L'Hopital rule. So when you find limit, for example, limit, let's just say 0, and then you have something like this. Okay, when fx equals 0 and gx equals 0 at x equal a, for example, then it will be a 0 over 0, right? We call this indeterminate form. What is indeterminate forms, I will explain later on, but I will just showing you a brief preview. So usually, because you learn in high school, sometimes there is no systematically or there is no maybe the explanation is not enough sometimes, or maybe you are not really understanding the subject for the limit, L'Hopital rules, and so on. But you know how to apply this. I'm sure. So whenever you find this 0 over 0, you can apply the L'Hopital rules. Okay, your teacher said that. And it's true. It's true. In a sense, it's true. It's true. So if you have 0 over 0, what you can do is, let's say this is the f of x and g of x. What you can do is you have limit, let's say x going a, and then you can do the derivative. Although we haven't yet reached the derivative part, but let me just show you what went wrong with these situations. You're doing this, and okay, you say that, oh, I can do this, and then the more if it's still 0 over 0, you can derive as much as you can until you get the result. Okay, and sometimes, because I also experience this kind of L'Hopital rule, and then okay, what you need to do is just derive top equation and bottom equation, and I will get the result eventually. But that is not true for all cases. For example, if we have this, what's the result? You have limit, okay, as x approaching 0, and you have sine x over x. Do you know the result? Yes, the result is 1. The result is 1. But if I'm asking you why it's 1, why? This is actually we call this is a part of definition in limit, and also part of definition for trigonometric derivative. Later on, we will learn this. Okay, but do not do this. Okay, so don't do this. So okay, you see here, you see the 0 here, you see 0 here. Oh, this over a 0 over 0, right? Oh, why don't we derive, right? So derives sine x and derive the x, and then you get, oh, it becomes cos x, right? Oh, it's 1. Wow, it's 1, right? Same here. Although it's the same and correct results, 1, but this process is wrong. This process is wrong. I'm saying that the first time the previous one, I said that when you have the 0/0, you can use L'Hopital rule. Okay, this is a 0/0, and I'm using the L'Hopital rule. What is wrong with that? Right? Probably you're thinking, oh, what's wrong with that? So first, the correct way in mathematics or in calculus in general, you need to know the first is the real concept, and then especially for the definitions. Okay, so it's called, if I want to write the terminology or the terms, it's called the circular reasoning. Okay, what is circular reasoning? So circular reasoning is, in this case, L'Hopital rule use the derivative, right? And how to derive is basically based on limit. Later you will learn. Okay, so derivative. Let me write this as just rough writing from me. Derivative is based on limit. Okay, and L'Hopital rule use limit, use a derivative. Okay, so which one is the first step? Should be this one, right? We need to understand the limit first, and then we apply to derivative, and then you are using L'Hopital rule and using the derivative you know before, right? Yeah, later I will show you, but please listen to this first. Okay, so the circular reasoning means when you have this 0/0 and you have these conditions, okay, you must know this condition here. So let me write here. So limit x approaching zeros of sine x over x equal 1 is part of the definition of trigonometric derivative. Okay, you got that? So you cannot use the L'Hopital rule here because it's breaking the rule, because this itself is the definition. So you need to find a more convincing way to assure that this is true. Okay, because L'Hopital rule is using derivative, and derivative for the sine is basically based on this definition here. Okay, and later on, if we have time, maybe at the end of the lecture today, I will show you how to make a good concept for proving this limit. Okay, we will use the geometric, and it's called the squeeze theorem. I believe some of you already have, maybe you have familiarity, or you have heard the squeeze theorem. Okay. Okay, but if we don't have time, maybe next week. Okay, but this is how to prove. Okay. All right. I don't think this is important to take notes for now, okay? Because later I will get you into this whole situation again. Okay, this is just to show you that if you know like limit and you want to use L'Hopital rule, you cannot use like casually, like okay, if it's 0/0, you can use that. There is some situation that you cannot use this. Okay. All right. And for your information, all the notes, okay, after we finish the limit, and move on to derivative, I will give the notes to you. Okay, so the PDF file I will upload on Moodle, and also, by the way, I need to remind you guys. Okay, I need to remind you we will have the circular reasoning. Okay, the simple way to say why is it circular reasoning is because this limit here, sine x over x, is the definition of the derivative itself. You know what I mean? So it's like breaking through your definitions. It's like you are circling around and you don't really get why you are doing that. Okay. So L'Hopital rule, you can use it because you know the derivative, right? And the derivative, you are using it because you know the limit. The limit of sine x basically is based on limit as x approaching 0, sine x over x equal 1. It's based on that. That will be in the chapter derivative. But actually, that's a part that make this a whole thing circular reasoning and without any conclusion at the end. So like you are going from here, we can use derivative because use derivative, or we can use derivative because limit, but you are finding the limit and using the L'Hopital rule. So it's like moving around here and you don't have any conclusion unless you have proven before without L'Hopital rule, okay, this is true, and then we can move on and we can use the L'Hopital rule. Okay, so in this case we need to prove with another method. Okay, all right. What I was going to say before is I need you all to apply the Google account. Yes, Stephen, correct. That's what I mean. Okay, correct. Correct, Stephen. Okay, now you are I think you need to as soon as possible to apply the Google account, or it's called also the GApps account. So it will be gapps.ntusc.edu.tw. I think some of you already applied, and it is helping a lot. Okay, because I will use also the Google Classroom, especially if I have some exercise for you to practice, because we don't really have much time in this semester because we only have 16 weeks and I need to skip some chapters, and maybe I will make an additional video for you. Okay? So you need to join the Google Classroom for assignment and some exercise. And also it's helping me a lot when we are dealing with the lecture, because if you are using the regular Google, like just usual Gmail, I need to admit all the students one by one, and you need to wait, right? You need to wait for the permission. If you use the Google account, you can join the link directly without any of the permission. Okay, and also I think this is good for you because it has a lot of storage for cloud. So you have more options to save your files. If your laptop is getting maybe full, like your hard disk or your SSD maybe getting full, you can store in the cloud for the GApps, for the Google account from the NTSC. You can apply. Oh, Helena, if you already have the GApps, when you are entering the Google Meet, you can switch account. And you don't need to ask for permission. So you can switch account to your GApps and then click the Google Meet, because usually when you click the Google Meet, the Google will find an account that are frequently used. So you can change the account. Do you understand what I mean? You can change the account if you want. And if you already have the GApps, please use a GApps account instead. Okay, it's helpful. Okay, right. Okay, that's some information. Also the university situations. Actually, the classroom for lectures is ready, but not for us, I think, because the ratio for the number of the students in calculus class is too much. So we will not get physical lectures, offline class. So we will have an online class for the whole semester. But we will have the offline exam. Oh, that's the link. Okay, thank you for sharing the link. So you can click the link, and yeah, maybe you need to translate. I think just using Google Chrome and translate the web, I think that's already okay. Well, we can understand what it is in the website. Okay, that's the link. So everyone look at the chat box and look the link at the bottom. You can try to look at, and maybe you can, after my class, or maybe tonight, you can try to apply. Okay, try to apply and register. All right, so we will still have online lectures the whole semester, and we will have the physical classroom for exam. Okay, but I will announce, like, maybe officially when we will have the physical exam. Okay, I think we'll only have physical exam for a final. For the other one, like quiz, midterm, we will still using the online system, and I will find a better platform to take the test. Okay. Yes, Helen. I think final exam on January 2022. Everyone already here, right? Or no? Do you think so? January 2022. Do you think everyone already here? Probably yes, Laura, for the final to be offline. The rest will be on online lectures. As I know from a few days ago. Yeah, and that's not about the number. How do you decide the chair inside the class? Because the university has now official policy, and we still too much. If we're less than 20, maybe we can, or maybe 30, less than 30, I think we can. Yeah, because we needed to have the social distancing and so on. And in the classroom, there will be a QR code now, and you need to scan every time you are sitting on the chair. You need to scan the QR code. Yeah. Okay. Right. I hope, even though it's an online class, I hope everything is okay. And yeah, I'm always open for you if you have something to discuss or any questions. Okay. Okay. Let's go back to the lecture. Okay. So right, this is just for your information. Okay, just for your information about L'Hopital rule, and you need to use it properly, appropriately. Okay. Okay, let's go back, and then let's think about one side limit now. Okay, so from previous slide, or from previous notes, I'm saying that we can approach the limit, right? We can approach from the left, from the right. Okay, that is if you are only approach from one side, that's called one side limit. Okay, let me just give you an example. It's called the heavy a function. Okay, this is called the Heaviside function. It came from the electrical engineer named the same person, Oliver Heaviside. This function is used for to describe describing the electrical or electric current, and switch at uh, at time t equals 0. Okay, so when we are looking at the graph, so this is the okay. And we have this. Okay, so this is 1, this is 0. So this is how, if we graph this, so this is maybe you can just call not x but just t, to directly t. So at t equals 0 here, we have two conditions, right? We have or if we look from left and we can look from right, it has different number, right? The left we are approaching 0, right? And the right is approaching 1. That's a totally different number. So there is no single number that the function approach as t approach 0. So limit t equals 0 of the function does not exist. This because so if I'm writing with negative here, that means we approach 0 from the left. Okay. And this positive means we are approaching from the right. Okay. Okay. Because this is not equal, so limit is not exist. Okay, in mathematics or in calculus in general, you can write this first, this, and last one is the conclusion. Or you can write the conclusion first, and then you can write because blah, blah, blah. It's still okay. Okay. Now, the general definition, or we call intuitive definition. So limit as x approaching a of f of x is equal L. Or maybe let me write the left-hand limit first with negative there. This is called the left-hand limit. And this is x approaching a from the left. And we call this a right-hand limit. And this is x approaching a from the right. Okay, I think, yeah, I will stick with this approach and definition for this one for one side limit, because I think if you read the textbook, I think it is using a lot of terms that I think it will be very difficult if you read that one. Okay, and then I will go back. I will go to the next page. Okay, so left hand limit, right hand limit. Okay, and then the conclusion is this. So if you have this limit equal L, this is true if and only if okay. Now this is important. Okay, so this is important conclusion.
Professor, can I
Yes.
ask a question?
Okay.
So you said that the limit of fx at the value when it approached to a and it had the value L, but what if like from both sides the value of that limit is L, but when the function at a is had different value, is it called also have like a limit?
Yeah, it has, like, for example, let me draw for you. You said that maybe maybe here, and you have another here, right?
Yes.
Yes. If we are going from here, we're going from here, and we all have this definition correct, right? Limit to maybe this is A. Okay. So from right approaching to A, it has the limit here. Let's say L. It has limit. Okay, it has limit because the limit from the left equal limit from the right. Okay. Although we have maybe this is B. Okay. Although F A is B, it's still correct. It's still correct. Still correct. Still, this is a limit. Okay. So this is quite interesting because, like I said before, the limit is something that actually you cannot really see because it's very, very small. Like I'm telling you the 0.99999 situations, right? But because most of us in this university in the classroom here, most of us will be an engineer, and engineer usually they are using some approximation, some numerical method, and the limit will be very useful for that. So we can be very, very I think I've shown you before when we are dealing with the real graph. So if you have a real graph like this one, or maybe, for example, let me show you the sine x over x. It's quite interesting if you're just looking by the graph. Okay. Okay, we have this still empty. Let's just write the right. Now, if you look here, it's interesting, right? Because we know from the graph, the limit is actually getting to 1. So we can also, another method, okay, aside from the geometric method that I'm telling you before, I told you before, we have also a method for trial some numbers. Okay, so we can use the table values, and we can use like some x from x equal 1 to 0, maybe 0.1, 0.01 is 0.001, and so on and so forth. And it will getting closer to 1, maybe 0.99999 something. Okay. But trust me, when you're zoom in all of this curve, at one point here, maybe at 1 pixel, exactly 1 pixel, you will see some distortion. And that means there is some undefined or some undefined situation on that point. Okay, but if you look in the global way, there is nothing wrong with the graph, right? Okay. That because the real world or the undefined one, the point is really small. It's just like 1 point, and you will not see that. Okay, so limit is actually helping us to simplify the method to see more clearly what is going on. Okay. All right. Okay, let's go back to our lecture.
Thank you for the answer.
Okay, sure. You're welcome. All right. Okay, let's see some example here. We have now a function g. You see the graph is quite interesting. We have a gap here, right? And we have the situation like the previous situations here. Okay, so let's try to look at some questions here. All the questions are approaching 2 and 5. Left, right. Okay, so let's look for x equal 2. Here x equal 2, and this is x equal 5. The first case for approaching number 2. So we are approaching from here, right? Going from here, actually. Okay, so here, and then the second one is from here. Okay, so we have 2 different results. The first one from the left is getting closer to 3, right? And from the right, it's getting closer to 1, right? Because this is not the same, it's different, right? Different result. So you can write it doesn't exist. And sometimes you can just write the NE, meaning the limit doesn't exist. Okay. All right. I think that's pretty obvious if you see the difference, right? And here we can look at from the left, okay, or to 5 here, and from the right, it's getting closer to. Let's say this is equal to. Okay, let's say this is equal to. From the left, it's 2. From the right, it's also 2. So the limit will be equaling to. Okay, despite the fact that the f or the g, no, sorry. So the g at 5 is, how much is it? Maybe, yeah, maybe 1. Yeah, maybe 1. Not 2. Okay, and this is not the same as 2, right? Still, the limit exists, and we can say that the limit is approaching number 2, right? Okay, that's one fundamental concept in limit. Okay. Another one that is also interesting. If you have limit as x approaching 0 for sine pi over x. Now, it's not sine pi but over x. It is sine, and I will maybe making bracket here to make it obvious that the sine is a function. Okay, so sine pi over x. Okay, not sine pi over x. Okay. So if you look here, the interesting part is if you maybe thinking what kind of sine results that is easy to take. the previous screen. Which one here? This one? Which part you are? Okay, okay. All right. Now, sine, if we are maybe taking x equal 1, okay? So we will have sine pi, right? And it's 0. Agree, right? Agree, 0. And then if we are taking maybe x equal half, maybe it's sine 2 pi, another 0, right? And maybe x is equal 1/3. And it is already 3 zeros here. And maybe from this table value, maybe you are okay, convinced that okay, maybe it's approaching 0. So maybe the limit is maybe 0, right? Probably, okay. But I must tell you that you need to be careful from here, right? Uh, if you look at the real functions, let me just if you look at the graph, let me make this invisible. And okay, if you look at the function itself, what you are seeing here is before the peak or the amplitude is quite large in the difference, right? But it's getting closer, right? Each peak, you see it, the peak getting closer and closer. And when you're approaching 0, you will see that if you zoom in and zoom in, it will be like never ending stop, right? It will be always having the peak, right? It's going up, it's going down, it's going up, it's going down, right? And when you going closer, it will still going up and down when you close to 0. That means we are not having any result from here. We are not having any exact number. It's still going from 1 and -1, right? And that is something that you need to keep in mind, okay? Every time you have a limit in a trigonometric function, you need to know at least the behavior of the functions, okay? It sometimes it's help you to understand what is going on. So sine, if you remember, if anything here, any variable, what you need to remember is it's always +1 and -1 for each the peak. Okay, so the maximum number is +1, the minimum number is always -1. And this is also happen in these situations. Okay, so you can say that the limit of sine pi over x does not exist. Or you can simply write d and e. Or you can write because if you want, the value of sine pi over x oscillate or keep changing between 1 and -1 infinitely as x approach 0. Or I think you can just simply take this as the answer and maybe just saying that the value is keep changing. That's also okay. All right. Okay, this is sine pi over x. Okay, the next one will be the infinite limit. Okay, let me show you another graph. One more. Let me make this invincible. Maybe making 1 over x. Okay, let's look at this graph here. The graph is 1 over x squared. Okay, let me zoom out so you can see what this look like. So it's like having really, so from the left it's going up, right? And from the right also going up, and then it seems they never stop, and then they never going to intersect, right? They don't have any intersection at all. They just going up as the x approaching the 0, right? It's still going up, and we call this the infinite limit. Okay. And let's go back to the notes. Yes, we call also unbounded limit. Yeah, infinite limit, unbounded limit. There is no no bound there, right? Okay, maybe wait. Yeah. So let's say this is y equal 1 over x squared, what we have seen before. And when we are thinking about the limit as x approaching 0, from here, and also if you want to be like maybe having some proof from or intuitive proof, like from the table, we can also write this in terms of okay, let's say trying plus minus 1, and then we can try plus minus 0.1, and then try until maybe plus minus 0.0001, and you will have really large number here, which means that the number that are going to be counted here will be never stop, right? It will going to be increasing, or you can say it will unbounded. Okay, it will be unbounded. So we will have this notation, or let me write in limit terms, is infinity. Okay. Yes, positive infinite, or yeah, we can write positive. Okay, but this is also positive, right? But remember, okay, this is, I think sometimes you forget, students sometimes forget that the infinity, although we are counting numbers here, like here we going from 0.001 and then going to be like million, 10 million, 100 million, and really a lot of numbers. But because it's going to be increasing over time, increasing, we are not sure how much this is, right? How much, right? So because we are not sure how much, we develop this symbol. So this is a symbol, okay? Not a number. This is the important concept. Infinite is a concept. It's an abstract, not an exact, not a number, okay? So when we write this is actually what the definition is, okay? As x approach 0, the limit, or maybe just maybe limit, the function, maybe just write the function 1 over x squared is arbitrarily larger and larger. Or maybe this is too difficult. The word is too difficult. Maybe just is tend to be, or maybe tend to become. I think that's a bit better. Tend to become larger and larger. That's the meaning. Okay. And this larger, it can be also, we can write increase. It's increase without bound or unbounded. Okay. Now the general definition, let me write in the intuitive definitions. So why we call this intuitive? Because we are only looking at the graph, and then we find the conclusion, and then we write the definition. We will have later the precise definition, but I will skip in the live session. I will write maybe another additional video so that you can watch later on. Okay. I hope this week or maybe next week I will upload on the Moodle. So let f be a function. So usually in math or in calculus, we usually start off our definition with writing what will be written. Maybe function. What kind of function? Let's just say using an f or g or h. Okay, usually like that. Let f be a function defined on both sides of a, which means you have left and right. Okay, except possibly at a itself. So it can happen, right, when the value is different. And then the limit will be means that the values can become larger as large as we please. So we can make it in any large number by taking sufficiently by taking x sufficiently close to a but not equal a. That is pretty much what we have looking at the 1 over x squared. Okay, when we getting x close to 0, we will get a large number, right? Large number. If you look at, and let me just make some a random graph. Now we will have a line here, the consequence. Okay, So this will be a consequence, implication, and implication. Implication will be there will be a vertical line, or we call this an asymptote. X equal A, okay, as an implications. Okay. All right. Another point from here, we can also have the opposite sides. So it's not only the positive infinity, we can also have the negative one. Okay. Let me write in another new slides. Okay, let's say that it's our functions there, and we also have the asymptote. Okay, and here is the limit as x approaching a. As it will be a negative infinity, so it will be going down here. Okay. So we will have this means is become negatively larger. Okay. The other definitions the same as the positive one. Okay. But the difference one here, it became negatively larger as x closer to a. Okay. Okay. Now to have the asymptote, okay, okay, to have vertical asymptote x equal a, at least one of the following statements is true. So you need just one to make the asymptote. This is the negative one. Okay, what does it mean? So it means that you will have if you have the just only one, like maybe like that, and you will still have the vertical asymptote here, right? Or maybe going down. Okay, you'll have the asymptote here. Okay, at least this one of these followings will have the vertical asymptote. Okay. Okay, how about we have the how about this function? Okay, let's just graph this in the let's just graph in the GeoGebra here. And let me write 2x divided by x minus 3. Right. Now we have interesting graph here. So if you look from the left, it's going down. If you look from the right, it's going up, right? So this is quite interesting. But it has the same asymptote, right? It's x equal 3. Let me write the x equal 3. Yeah, that's our asymptote, right? You look at, okay, that's true. When it's going to approach 3, it's getting negatively large, right? It's getting negative infinity. When it's going to be, when x is getting closer to 3 from the right, it's getting a positive, right? Positive infinity. Okay. Right? So, let me make some. So in the 2x divided by x minus 3, we have vertical, or let me write just vertical asymptote. Or I will write VA later in the next terms, okay? And you will know VA is vertical asymptote. Vertical asymptote is x equal 3. That's true, right? But how about limit x? So limit x approaching from the left. We know that from the left, there will be negative, right? Negative infinity. And from the right, so because this is not the same, right? This is not the same. So it doesn't exist. Okay. It doesn't exist because of different behavior between the left hand limit and right hand limit. Not because the infinity. Okay. So this is because it's not the same. Okay. Okay. Any question from here?
Yes, sir. Can we say that we don't have, like, the limit doesn't exist because both sides limit have different value?
Yes.
Okay.
Of course. Yeah. Of course, you can say that also. Yeah.
Okay, thank you.
Okay. Okay. The next part, this is actually 2.2 limit of a functions. The next part is the limit law. Okay. So how we are going to use limit in our mathematical notations if we want to simplify, to make it into, maybe if we have limit and then we need to plus the limit with other limit. Can we do that? Okay, I believe you already learned this, but I will just show you what is the thing that sometimes you forget for the limit law. Okay, so first thing, suppose C is a constant and limits also another limit. So we have two functions f and g, both have limits and both limit exists. Okay, both limit exists. Okay, now let me write with the red one. So this should be really keep in mind. So you need to make sure that limit of f of x and limit of this gx, they both need to be exist. Okay, first that is the condition, and after that you can do this, all the computational with limit. You can plus, and then you can also minus. I will just write minus below here. Okay, I hope you understand what this it means. So it means that you can also minus. Okay. Second one, you can factorize any constant you find in limit, and you can remove that constant out. And we can multiply. And this is, I think, sometimes you forget this, the last part here. This need to be, have some restriction. It should not be equal to 0. So that is, we can do all the calculation here. Okay, so all the calculation here, it's become logic and makes sense if you are having both limit exist. Okay, so because both limit exist mean if they have the exact number, right? They have the exact number. So that's why you can plus, you can minus, you can multiply, you can divide, and divide as long as the g is not 0. Okay, so this is basically true when the limit of f and limit of g, they both exist. Okay, that's the first thing. All right, let me go to some intro example. Like looking at this function here, we have the red curve, the f, okay, and the blue curve, g, okay. And let's look up the question here. We have limit as x approaching -2, so probably here. So first, for the f, let's move on here, right? And we can write limit, because both sides approaching the same value, we can simply say that as x approaching the -2, f of x, it will be resulting 1, right? And g is around here. It's also getting the value for g is getting -1, right? So we can simply say that, oh, because this is limit x -2 of f of x plus 5, we can write this. And because limit as x approaching -2 of f of x is 1, we can plus 5, and then this is -1. Or we can simply write -4. Okay. Blessing, you need to...
Professor, I want to ask. I'm still confused at how you like defining if this function is approaching something or what, just by seeing by the picture, just by seeing the picture.
Oh, okay.
I mean, like, okay.
Let me explain one more time. Okay. Now the question is this one. Okay. As x approaching -2. Okay. -2 is here, right? Around here, right? And we have two functions. First is f. The second one is g. All right. Okay. Let me erase this part first. Basically, we want to approach this -2, right? This -2, we can approach this, right? And we can simply look at the functions. And -2 is here, right? It's around here. X -2. Right? For the x. So we can going from the left side of that -2 from here. And we are going from the right. Okay. And it's actually going to be 1. All right. The same thing for the other function g. It's same -2 here. And it's around here, right? We are going from the left and we are going from the right. And we are going from here. We are going from here. And it's approaching this number here, which is equal to -1. Is that clear enough, Blessing? Do you get the idea? Okay. So that's how you are looking at the graph. Okay. And slowly you can see the easiest way is just looking the x first, because sometimes when you are not really familiar on how looking the function and the graph, first you need to look at the x first. And look when you have this exact number like -2, which one is the function? Oh, here. Okay, so this is maybe, oh, here. Oh, this is -2. Oh, this is its functions, it's f, and then the other function g is below here. Okay. All right. So the idea of the limit law we can apply here, and we can simply say that okay, it's -4, and we can calculate all these questions, right? And how about the limit as x approaching 1? Okay. Now we need to look for this 1, right? 1 is here. Let's look for the f first. I think it's quite easy. We are looking from the left. We can looking from the right. And it's around what? 1, 2. Okay, probably it's 2. Okay, it's 2. From the table, from the graph, we know it's 2. And then we are looking from the other function. So going from the left, going from the right. So the other function is here. Oh, let me right here. Oh, there's something wrong with this one. If we are looking from the right, it's going here, which is -1. But if you're looking from the left, we are getting different answer. It's -2, right? So we can simply say that limit as x approaching 1 for gx, it doesn't exist. Or you can also write from the positive, from the right side, it's not equal from the left side, right? Or if you want to write in more details, like maybe you write the left is -1, and then you write from the left, this is -2, and then you can simply say, okay, this is not the same, and then limit doesn't exist. That's also fine. You can write 1, 2 here, or you can write until the very detail. That's not that all still okay. Okay, all still okay for me. Okay, and because of that, because it doesn't exist, the whole thing doesn't exist. Okay. All right. The third one, we have limit as x approaching 2. Okay. For f of x over g of x. So we need to find number 2. Number 2 is here. Okay, that's 2. Okay. Let's look for the x from the left and from the right. For the function f, we got here maybe around 1.5. Let's say it's 1.5. Okay. That is actually my assumption. Let's just take 1.5. Okay. And then at the other function here, if you look here, it's getting 0, right? It's getting 0. So here is 0, right? So we have 1.5 and 0. We got the results. But when we are looking here, it's f over g, right? So when we write this, this is around 1.5 and this is 0. That is becoming wrong solutions. Okay, you can simply say that this is not exist. Or if you want to write the complete answer, the limit doesn't exist because the denominator approaches 0 while the numerator approaches non-zero number. All right.
Prof, can I ask something?
Yes.
So you have like one graph there, and you have more than one limit function. So, I mean, like, how do you determine this function in the function position on the graph while there's more than one function? Well, you just have like one picture there. It's one that I'm confusing.
There is two functions. There's two functions. Why we say one function? We have two functions here. F
I mean, like,
and G.
I mean, like determining the position of the function in the line. I mean, like you should, yeah, the position. I mean, like this function is in this area of the graph, while the other function is here.
But that's from the limit, from the x.
Oh, okay. Okay.
Do you get it?
Yeah.
Do you get it?
Thank you, Professor. Yeah.
Okay. So here's the thing. Okay. So first you need to be familiarized with the function. Okay. Like I said before, for example, this -2 here. Okay. Let me just erase this. First, you need to find where's -2. This -1, -2, right? Okay. First case, you're going up because this is your function here, f, right? The red curve here, the red curve. Okay. And the other functions, we need to going down here. It's the g. All right. And you need to look one by one from the left, from the right. and look one by one from the left, from the right. One function and one function. Okay, function f is this, function g is this. Okay, and the other number one. Okay, function f here, function g here, right? And we have 2 here, right? Okay, and x equal to, we have here, right? And we have also here. That's the functions g, right? The blue color here, the blue curve, is also g, right? Okay.
Okay. Thank you, Prof.
Okay. All right. So okay, that is basically the how we are using the limit law on some graph and some questions here. Okay. Okay. I will add some additional law for the limit. We call the power law. Limit as x approaching a. So we have some n as our power for the functions, and we can have this. So this is basically when we have we use the product law, and if f of x is equal g of x, then it will be the multiply of itself, right? And we can write as a power. So we can write this as a power, and the n should be a positive integer. And the second one, we call it the root law. And also positive integer. Why it cannot be negative? Because if you make it negative, it will be a mix between power and root, right? So I will make it just separate. All right. The other one is if you're just having the constant, it's just a constant. Nothing wrong with that, right? And if you have an x, you can have a. And we can use this also in the to solve some limit problem. Okay. And from here, from this limit and the power law, we can have also. So this is the power law. So we have x with the power of n, and you know that limit x approaching a of x is a itself. So we can say that this is actually a with the power of n. And also we have for the root law, it's also apply. Okay, it's also apply. So basically, when you have something like a limit as x equal 5 for 2x squared minus 3x plus 4, actually the steps when you are thinking the law, before you try to substitute, what is happening is you are going through this this concept first. It's becoming constant, it's becoming 3, 5, and it's becoming 3. Okay. So basically what I was going to say here is we can evaluate. So first, we can evaluate limits by direct substitution. So let me write here, if f is a polynomial or a rational function, and a is in the domain of f, then limit x approaching a of f of x is equal f of a. Basically, what I was going to say is you just plug in a inside the functions and you will get the results. That's one way to see. Okay, one way to see. Okay. Okay, let me write how to evaluate limit in a conclusion first, and then I will show you how. I think because in the textbook there is a lot of words, and I need to summarize all of that to you. Okay, so to evaluate limit, so let me write how to evaluate limit. First is direct substitutions, right? Which means you are just plug in the x value. Second, evaluate first, and what is the results? And then the third, is it indeterminate form? Indeterminate means 0 over 0. Okay, so let me write the diagram. So first, direct substitution. Okay, so first direct substitution. So limit x a fx. Let's just write this fa and try to evaluate the fa. And then we have several possibility. Okay, the first one, your fa becomes b, become a result, exact result b, which means we done here. We get the answer we satisfied, right? Yeah, we satisfied. And then the second one, we get the rational b over 0. And probably we will have a vertical asymptote, right? And the limit will be unbounded, right? And the third one, we can have a 0 over 0 situation. Now, before we learn the L'Hopital rule, there are several methods that usually you can use to check or to find the limit value. So first, if you can factorize, you need to factorize. If it is a quadratic, you can factorize, right? Factorize. Number two is conjugates or rationalize. If it is the rational function and you have usually a square root, you need to multiply with the square root, right? And the third one, if you have a trigonometric, you can use trigonometric identity to solve it. And the last one, you can use approximation if you want. Like you can use stable value, and like maybe sine x over x, you want to use stable value. Actually, you can also do that. And probably L'Hopital rule. I will put this at the last effort. But I believe factorize, conjugate, trigonometric identity, and approximation is a better way to approach before you're learning the L'Hopital rule. And sometimes factorize, conjugates, or trigonometric identity, the method will be sometimes it's faster, sometimes. Yeah, sometimes, not always. All right. So still, you need to have some result there. Okay. And also, all this method is not no need to memorize. You need to have some practice, I think. Okay. All right, let me give you some example for this, at least factorize, conjugate, and trigonometric identity. Okay, we still have time. Okay, we still have time. Okay, for example, limit as x approaching 2. Okay, try that one. And the other one is limit okay, let's just have two function two limit questions. All right. First thing, both of them, we need just to check what will happen when you are plug in the functions. Okay, you plug in the function, it's getting a 0 over 0, right? 0 over 0 situation, and that's why you need to think which method you can do, right? Yeah, okay. 2, yeah, it's become 2 plus 3, right? 5. Okay, so first, this is also interesting. If you have x squared plus x minus 6, let's say this is f. Okay, let's say this is f. Let f is this function. Okay? And then you try to solve and look for simplifications. You can factorize this, right? Easily factorize. Oh, you can see that, okay, x minus 2, x minus 6 is I can cancel this. Oh, and then you can have this. And then I will ask, like in your small quiz, is it the same? Right? Is it the same? It is not the same. Okay, it is not the same. You simplify this, but in terms of functions, because you are making this as a functions. This is a different functions. So sometimes, to help you think clearly, let's make another functions, g, for example. So f is this, and you let gx is equal x plus 3. This is just to help you stay on the road, okay? In terms of equations, this is correct. But in terms of a function, this is different, okay? All right. Or we can say that, yes, this is f, right? So f of x, it can be x plus 3 when x is not 2. But it will undefined. if x equal 2, because the domain is different. Do you get my point? Do you get my point? Why this is not the same? The answer, the simple answer is the domain is different. Okay? I hope you get my point. Okay? But the answer, when you get this x plus 3, we just get that limit, or let me write it. Let me write this. Is the same as limit. Now this is correct. Now this is correct. Remember the limit concept. Okay, the limit concept. The function itself may be different, but the limit, because it's approaching the same number, that is correct. Yeah. Yeah? You want to ask something, Laura?
Yeah, Professor, you said that they are not the same as
Yes.
a function,
yes.
but they are the same as an equation.
Yeah, in terms of just general equation without thinking anything about functions, yes.
Okay,
Yeah.
thank you.
But I think the most important thing is at the limit. Okay, at the limit, if you have the limit, then this is true. Okay, this is correct. Okay, this is true. Okay. And if you want to find the limit, you can just find this limit x2 x plus 3 is 5. Okay. Okay. So probably the university is not about, for mathematics or calculus, it's not about finding this 5, not about all of this, but this, all this process. Okay, so sometimes when I have questions like in really long writing, this process becomes more important than the end results. Okay, so if you have the different end results, but you have a good way of answering, of explaining, you still get a point. Maybe not a full point, because the end result is not this the answer. Okay, so this I think it's more important. The logic behind the process is more important. Okay, let's move on to the other one. The other questions, you see that if we plug in -1, of course it will be 0 over 0, right? So what will happen now? We can use the rationalized method. So how rationalized method works? If you remember, you have maybe 1 over square root of 3. The first question, can we use derivative? Why you need to use derivative? Why you need to use derivative? Technically, you can use that, but in terms of our lecture now, we are not getting the derivative, right? So okay. We will learn the derivative parts later. Okay, the derivative you mean is called the L'Hopital rule. Okay, it's already I mentioned before, but I will not saying any explanation for now. I will explain it later. Okay. Okay, back to the rationalize here. You can rationalize and multiply with the same square root like this, and you will get the standard form. We call this the standard form. And you can also do this, and we are multiply the equation here with the and then we get that. Simplify this. Okay, we get this result. And again, this might a different functions than the first one here, although we are just simplifying this. Okay, this is a different function actually. Okay, actually. So limit as x approaching -1 is 4. Okay. When x is not equal 1. Okay. When x equal 1, it's undefined. But the limit is equal 4. Okay. Okay, maybe last one for just example. For trigonometric part, let me give you this. Okay. Plug in here, plug in here. Of course, you will get 0 over 0. Then you need to think. Maybe you have some identity to check, right? I think the easiest one is just thinking about the sine squared plus cos squared is equal 1. And then you can use that to substitute the sine squared. So you will have or maybe you can let this as a function first. And you know that this will be 1 over 2 plus 2 cosine theta. Okay, the function. And then the limit is 1 over 4, but theta theta is not equal to 0. Okay? Because if you have 0 here, it will be undefined, right? Okay, I believe this will be the last part for today. And okay, I need some feedbacks from you. So let's go to scan the QR code. I'm sorry if it is a little bit troublesome for you or bothering you or make you feel boring, but I'm trying my best to have some engagement with you. So one of them is using this kind of platform. Okay, so please scan the QR code. All right. Okay, joining. Okay, let me mirror the other presentation. All right. You can go to the website if you have difficulty to log in through the QR code and use the code 88729485. Okay. We're waiting for several students. Okay. We have in class now 48 minus 2 from me, so 46. So yeah, 7 students. Okay, 6 students left. 6 students. Okay, so how long we will going to have like this kind of feedback? Sometimes, maybe most of the time we will have. Okay. Sometimes just one questions and then just a feedback, or sometimes just a feedback. There's no question sometimes. Okay, but I will have some question now just to check whether you get my point or not. Okay. Okay, 42. Is there any students that haven't joined? Okay, I think I will start. Okay, I will start. And I will use the points from the small quiz to your activity. I hope you can get it. And also if you get maybe win the game for 4 or 5 times, or maybe 3 times. I will prepare maybe a gift. I will give those gifts when we have the physical exam or the physical class. Okay. Class start. All right. Is there any student that haven't joined? Okay, prepare your name. Actually, you can use any name, but it's better to use your real name and student ID. If you use your nickname, if you win the game, I need you to tell me your real name, okay, and also the ID. Okay, let's start. Okay. Okay, which one is true? ADF, ACE, BCD, ADF, BEF. Okay, 20 seconds. I hope the time is enough. I need to make some like restriction in time, because if it is too longer, or maybe like 1 minute, I think it's too long for a question like this, right? Okay, time's up. All right, good. Okay, most of you are getting what I'm doing. Okay. Who will be the first? Oh, Oogie. I don't know which student, but I will check later. Okay, get ready. All right. Question 2. All right, start. Okay, true or false? Okay, 20, yeah, 20 seconds. All right. I hope you get it right. Okay, 5, 4, 3, 2, 1. Okay, good. It's true. Remember, the function is different, but the limit is true. Okay. All right, let's move on. Whoa, now the fastest one. Oh, Jim. Now it's changed. Okay, last questions. Okay, let's see who will be the winner of the quiz. Okay, is it true or false? Okay, is it true or false? Read the question carefully. Okay, read the questions carefully. Oh, what's happened? Read the question carefully. Read the question carefully. Like it has the over 0, right? It has over 0. Of course, it will not exist. It is also 0 over 0, right? Okay. Wow. Oh, okay. It's coming back. Okay. Good. Okay, the last part is actually I'm saying like happy weekend to you guys, right? Enjoy your weekend. But for our course, unfortunately, you still have a Monday morning course. Okay. Okay, see you later, guys. You can leave the meeting. Okay. Yeah, you're welcome, Paris. Yeah, you're welcome. You're welcome. Yeah, you can leave the meeting, and some of the students will have the other course, right?
Hey, Professor, I want to ask you a question.
Yes.
So, because like I just kind of like understand the concept, but I have some trouble with my basic math. Like, should I like continue? I don't know about the exam. Is it like gonna affect me a lot if I don't know some concept like geometric or something?
Yeah, I think it will be. Sometimes it will be a trouble with if you don't really know the concept. But I think as long as you understand the idea behind the calculus, I believe it should be okay. Should be okay.
Okay. Okay. Thank you.
Yeah. Yeah.
Bye bye. Thank you.
Oh, Stephen, why the last question is true? Did I make the mistake? Actually, what is the question? Let me check. Oh, OMG, Stephen. So sorry, Stephen. Yeah, it's correct. It's 0. Oh, I'm taking wrong answer. Taking the different question. It should be not 0. It should be 2. Wow. Okay, I will fix this on Monday. Okay. Thank you, Stephen. Thank you, Stephen. Thank you. Thank you. Thank you for reminding me. Okay. 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 See you. See you on Monday. Okay. See you on Monday.